All right, welcome to another College Board lesson about the implications of intermolecular forces. We're going to do a real quick demonstration lab, and I'm trying to make this work for the online students. This is meant to be as a discussion, but you'll just have to work with me, discuss with your computer screen. Silver classes, I'm sorry, you have not actually, that would be my second period. You have not seen intermolecular forces before doing this lab, but you'll still be able to get it. So the intermolecular force, that is not the force in Star Wars, but it is it is important to understand the ways of intermolecular forces, and it allows us to understand why substances are the way they are. Okay. So now we remember at the beginning of the year when I was talking about different states of matter, and I was talking about how you could change states from matter from a solid to a liquid to a gas. Well, this can be demonstrated going from a liquid to a gas as boiling, and then solid to a liquid as melting. And we can look at the strength of the intermolecular force and find those from their boiling points and melting points. So they're directly related. The strength of the intermolecular force is related to the boiling and the melting points. That's because as a solid, the intermolecular force is strong enough to hold the particles together. And so the particles are locked together tightly and strong enough to virtually lock them in place. So the kinetic energy of the molecules is not strong enough to overcome the intermolecular force strength. Now, as a liquid, it's able to start to overcome it. However, it is not completely overcome. The molecules will still slide past one another, but they're not able to separate from one another. Now, as a gas, they are able to separate them from them, and they have enough kinetic energy to overcome the intermolecular force. So the changes of state has to do with how strong that intermolecular force is. So we're going to take a look at a few different molecules and we'll see what we can compare. So first, let's just think. We have three different molecules here. We have this guy, and this guy. Now, how are these molecules different and how are they the same? Well, you could say that they have different lengths of their carbon chain. This one has one carbon, this one has two, this one has three. The different numbers of carbon or hydrogen, basically the same answer. You could say they have a different molecular mass. This one is going to weigh more than the first one. But what's the same about them is they all have this OH group right here. And that's going to be important. This OH group makes it an alcohol. All right? Now, what must happen for a substance to boil? Take a look at that picture and think, what happens when a substance boils? Well, that's when the molecules actually will separate from one another in the liquid phase to be a gas phase. So these molecules aren't touching each other anymore. They're more individual molecules moving around. Now, as a liquid, the molecules are represented as basically as a group. They're stuck together. Now, what is the difference between boiling and evaporating? Give that one a think. So, evaporation will take place at the surface. That's where where the vapor pressure is less than the atmospheric pressure, and so molecules that sit at the top. Let's take a look at that picture. Molecules that sit at the top can sometimes get bumped off and join the gas phase. They just one or two molecules at a time will get enough kinetic energy to leave. And so that's what evaporation is. Now, boiling is when all of the molecules have enough kinetic energy to leave. So the boiling takes place within all the molecules. That's why you get bubbles inside of the actual inside of the liquid, is because they're starting to turn into a gas even at the bottom. So just to prep you on this, those three molecules that we took a look at, those are the three we're going to investigate. And the first one is called methanol, and its structure looks like this. It is carbon, and it's called CH3. See how that works? OH. And this one is called C2H5OH. That's ethanol. And then this is called C3H7OH, and that's propanol. So let's take a look at our lab. So these are the three substances we'll be testing. We have methanol, and we have ethanol, or ethyl alcohol, and then we have isopropyl alcohol. And then we're going to dip them in some Q-tips and see how this works. So here are our three alcohols. We have methanol, ethanol, and propanol. You can see they're all different alcohols because they all end in OH. That's what makes them an alcohol. Now the thing that's different about them is that the length of the carbon chain. This one has one carbon, this one has two carbons, and this one has three carbons. So as we can see, which one do you think is going to evaporate the quickest? Whenever I take all three of them, wet them in their respective alcohol, and then wipe them across. We're just going to make a quick line. Which one do you think is going to evaporate the quickest? So that was a good 30-second lab. As you could tell, that propanol wins because it had the slowest evaporation. Methanol had the quickest evaporation. So that actually means that propanol has the highest boiling point because it takes more energy to evaporate those. It means that propanol has the strongest intermolecular force, and that methanol is the weakest intermolecular force. So we could demonstrate that by a quick three-part example. So this is what we were able to see. We were able to see that propanol has the slowest slowest evaporation time, which means it has the highest intermolecular force. Well, that is because it has the highest molar mass. Or molecular mass. It's the heaviest. It has more carbons in it, so it's going to be heavier. So it will also have the higher boiling point. So the higher the intermolecular force, the higher the boiling point. Now remember that is a really, 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 really good thing to remember. So you can tattoo that one on your forearm, I guess, since your forehead's getting pretty full. So now let's see if we can take this one step further. So we looked at alcohols in our lab. Now let's think about hydrocarbons. And these are just alkanes right here. Hydrocarbons that contain only single bonds are called alkanes. Now we're just saying that it has carbon to carbon and then just hydrogens all around it. This is called an alkane. And alkanes are highly combustible and valuable as fuels. So you have ethane, propane, butane, pentane. You've probably heard of the one that has 8 of them. That's called octane. You've probably heard of that one. So alkanes are a little bit lower though, and have this data right here. So what patterns would you observe with these alkanes? You have methane, ethane, propane, and butane. You can see that the length of the carbon chain increases. So what patterns did you see? Well, you could say that as the number of carbon atoms increases, the boiling point increases. But actually a better way to say that is to say that as the molecular weight increases, the boiling point increases. The heavier that the molecule gets, the boiling point increases even more. That's because this has a higher intermolecular force. Now, let's compare those. Let's compare methane that alkane that we had to methanol. Why is methane a gas at room temperatures, which it is, yet methanol is a liquid? Hydrogen bonding, the answer is. So, methanol looks like this, and it has this OH group right here. So now what is special about methanol is that it will do what we call hydrogen bonding. So another methanol molecule right here will have a hydrogen that will be attracted, because this is a positive charge, it will be attracted to these lone pairs right here. And so we'll get this attraction between a hydrogen and an oxygen. Now, to have hydrogen bonding, you have to have something, a molecule that's very electronegative, like fluorine, oxygen, or nitrogen. But this is possible. Methanol will do hydrogen bonding. However, methane will not. It does not have a very electronegative atom. It doesn't have fluorine, oxygen, or nitrogen. So methanol is hydrogen bonding, while methane only has very weak London dispersion force. So methanol will actually hydrogen bond twice with two other methanol atoms, and so that's why it is a liquid at room temperature, and why a methane is a gas. However, it's still not that strong because it was able to evaporate very quickly. So guys, just remember this. Remember, I just bring it back one more time, is that I remember that as the intermolecular force increases, the boiling point or the melting point increases, and vice versa. So now let's take a look at some of the different hydrides right here. Now we're going to look at tin, and we're going to look at all these in group 14. This is the carbon group right here. So if we look, and we're going to look at hydrides of them. So if we have tin hydride, and then we're going to look at germanium hydride, and we're going to continue down the group, and then we have silicon hydride, and then we have methane, or CH4, or carbon hydride. So you see that methane has the lowest one, and then tin has the highest one, highest boiling point. Okay, remember boiling point's on that y-axis. So as the molecular mass increases, you can see that the boiling point does increase. So you see that increase in intermolecular force because of the increased molecular mass. So now let's look at tellurium, another group, group 16. We're going to start with tellurium, and we're going to take a look at tellurium here, tellurium hydride, which is a little higher boiling point because it is a little bit heavier than tin. And so we'll get selenium hydride, and we'll get dihydrogen sulfide. So we have these three right here. The trend continues. Now we get to oxygen. Oxygen and hydrogen make water. So we have a very sharp increase right here. So water does not follow the rules because water is very special. Why do you think water has a higher boiling point? That is because it has a hydrogen bonding, which is a much stronger intermolecular force. Therefore, it will have a much higher boiling point. Okay? So that is why the trend does not decrease. Water has hydrogen bonding, while the rest of them only have weak London dispersion forces. You can even see this trend with all the different groups. With group 14, 15, 16, and 17, you can see that water has the highest boiling point, and we see these three guys right here because they are very electronegative atoms. Fluorine, oxygen, and nitrogen are very electronegative, so they will hydrogen bond. However, carbon is very lonesome. He was not able to hydrogen bond, so he has a very low boiling point. So hopefully we're able to see the trend between molecular mass, but we're also able to see the trend, the exceptions to the trend due to our hydrogen bonding. All right, have a great day.